This afternoon, I'd like to give you a short introduction to what we call phase diagrams for compounds. Okay. Now, this first one we're going to look at is a phase diagram for water. Now, what a phase diagram tries to put into a graph is the various pressure and temperature conditions when the states of solid, liquid, and gas are existent for a particular compound. This is the phase diagram of water. So here on the y-axis we have pressure, will be labeled here, and notice that 760 torrs, which would be considered standard pressure or 1 atmosphere, is labeled here. And then on temperature scale is on the the x-axis, and we've got Celsius here. And this is water. So this is the phase diagram of water. And so what we're looking at is this purple line that looks somewhat like a Y or maybe a wishbone shape. And you notice when you look at a phase diagram, there's 3 large zones or region. The region with the low temperatures and higher pressures. So this phase right here on the far left side of the diagram is going to be where your solid exists for this particular compound. So at all of these various pressures and temperature correspondence, we would find water in the solid, or what we would call the ice phase. And then as we see here in the middle of the wishbone, or the Y-shaped, we have the liquid phase. Okay. And then we have the gas phase, is always found on the far right side of the graph at higher temperatures, and also we've got some high pressures up here. But don't forget that you can have gases at low temperatures and really low pressures. They can also exist down here. So as we move along these line segments, these purple lines here, we have different segments. From here to what we call the triple point is the sublimation curve. These are the pressure and temperature conditions when we can go straight solid to gas or gas to solid. We can cross directly between those two states of matter, those two phases. We've got the fusion curve, or the fusion segment here, where we have various pressures and temperatures that we can transfer solid to liquid or liquid to solid phases. And then the third segment is right here, and this is your liquid to gas transition, okay, what we would call the vaporization curve, or the vaporization segment. Okay. Now also on a phase diagram, there'll always be this triple point labeled here, and notice that's where the 3 line segments, or the 3 curves, intersect. At the triple point, you will find all 3 states or phases, the solid, the liquid, and the gas, present in an equilibrium state. Okay, that's the triple point, so it's the intersection point between these 3 segments. And then also out here at the tip, where the gas and the liquid stage, you notice that this segment kind of stops right here and doesn't extend all the way out on the graph. That's what we call the critical point. Above the critical point, no matter how much pressure you put onto the substance, onto the compound, it will stay in the gas phase because it has such high temperatures. You're going to have so much kinetic energy that it is not possible to get that gas to condense back into a liquid phase or a liquid state. Okay? Now, one last thing I want to show you on this particular phase diagram is, when you're interpreting a phase diagram for a compound, if you will look at the fusion curve, or the fusion segment here, that segment between the solid and the liquid phase, look at the direction that it is pointing or leaning towards, okay? This would be considered to have a negative slope because it's leaning backwards, okay? It's a negative slope instead of a positive slope that would be increasing, okay? If you will look at that segment, it will help you make a relationship between the density, which is a physical property, of the solid phase and the liquid phase. On water, we know that solid ice cubes, float in water. So therefore they have a lighter or lower density. Okay? If this line is bending backwards, it has a negative slope, it's telling us that the solid phase or solid state has a lower density. Okay? This line segment here will be leaning towards the lower density phase. Okay? So let me give you another example of a phase diagram here on the next page of our book. Okay? Let's look at these right here. Okay, this one here on the left is of iodine, and this one on the right is of carbon dioxide. Now, while we're talking about the slope, the direction it's leaning, see right here this curve? See how it's leaning towards the liquid? Okay, towards the liquid, so that's telling us that it's a lower density. The liquid is a lower density than the solid. Okay, and notice over here on the carbon dioxide, it's leaning ever so slightly towards the liquid rather than the solid state. So again, we would say that the liquid phase has a lower density than the solid phase. Okay, and again, notice on each one of these graphs, we've got a triple point defined. Okay, we also have critical points defined. And notice that the shape is still similar in that it's a wishbone or a Y shape, but the amount of area that each segment phase is occupying is different. We know that gas for carbon dioxide is what we are most accustomed to, and iodine at room temperature conditions, it exists as a solid. Okay, so a phase diagram helps us see the various temperature and pressure conditions when the solid, the liquid, and the gas phase for a compound will exist, along with helping us to see the relationship between the density of the solid and liquid phases.